Okay, the limit comparison test, and the book mentions that this test is particularly useful when a sub n is a rational function of n. But let's look at theorem 11 first on page 530, and then we'll work some examples. It says in three parts. First, the limit as n goes to infinity of the ratio an over bn, if this limit is equal to c and c is greater than 0, then either both a and b converge or they both diverge. Now the reason that's useful to know, okay, is that normally when we're setting this up, we're going to know if b sub n converges or diverges, so that once we do this test and find the limit and c is greater than 0, because we know that b either diverges or converges, we know that a will agree if this condition is satisfied. So that's the first rule. That's the number one part of theorem 11 in this chapter. Number two, it deals with the limit when c is equal to 0. In this case, if b converges, then a also converges. So if b converge, a converge. And then finally 3, we have the situation where we get our limit is equal to infinity, and then we know that if b diverge, then by golly, of course, a must diverge. Okay, so the actual usefulness of this might become a little more clear if we work examples 2 and 3. Okay, let's get a little more paper out here, and we'll look at the first part, part A of example 2, and they have a series that's 3, 4, plus 5, 9, dot, 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 and this can be represented as the series n equals 1 to infinity of the rational function 2n plus 1 over n squared plus 2n plus 1. If you're confused about how this works, just look back at example 2 on page 531. Now the important part is that this whole rational function is equal to a sub n. And if you look at this, we can apply look at the powers here, and we realize that as this thing approaches a limit, the parts that are going to be important are 2n over n squared, and that's going to be 2 over n, okay? And we already have a pretty good guess that this is going to diverge, okay? But this leads us to the idea that we might want to use for b 1 over n is equal to bn. And then we know that this diverges. Now we can ask this question, let's make a ratio of these two functions. And on this first one, I'm going to write it out. It looks like this. That's a sub n, and then b sub n is 1 over n, okay? Now, of course, this is in the denominator, so we can take its reciprocal and multiply it by the top and the bottom. So then this cancels, and we have to multiply this by n, so we get 2n squared plus n over n squared plus 2n plus 1, and this is the limit we're going to evaluate. And of course we have a 2n squared over n, so this is simply the limit is equal to 2. Now if we apply rule number 1 from theorem 11, in other words that our limit c is greater than 0, and we know the original denominator bn diverges, then we know that the numerator diverges as well. Although we probably could have seen that one coming. I think the important thing to realize is the little trick that we're going to multiply both the top and the bottom by 1 over n and redefine the rational term in the numerator as this new combined thing, and then take the limit of it. Hopefully that's clear. We can work one more example. Next part of the problem, the example, part B, we have a is equal to 1 over 2 to the nth minus 1. We already know that 1 over 2 to the nth converges, and we can see that at a limit, when n gets very large, these two terms are going to be quite close together. So why don't we make this equal to b sub n, and this will be our a sub n, like this. So we can make a ratio of these two. We get 1 over 2n minus 1 over 1 over 2n. We do the same trick by multiplying both the top and the bottom by 2 to the nth power, and we get then 2 to the nth over 2n minus 1. And we can ask, at a limit, as n goes to infinity, what happens to this this term, and we can do a quick division, and we get something like 1 over 1 minus 1 half, 1 over 2 to the nth, and we ask what is happening at a limit here, and we see that as n gets very large, this goes to 0, so the limit here is equal to c is equal to 1. And then once again we can apply part 1 from the limit comparison test and say, because we know that b converges, therefore a converges as well.